Hi everybody, the purpose of this video is to go over section 1.6 where we will talk about the rest of the equations. We will start off talking about rational equations, and then we will apply that to an application, and that application will be work rate problems. We will then talk about equations with radicals, equations with square roots or cube roots, equations with rational exponents. Those are exponents which are ratios of two integers, and we will conclude with equations that are quadratic in form. So let's get going. So these are rational expressions. You can tell that because the numerator and the denominator are ratios of two polynomials. So unlike fractions, which are ratios of two integers, rational expressions are ratios of two polynomials. Now, if you have an equation where at least one of the terms is a rational expression, well, guess what? You have a rational equation. And here are two examples of rational equations. Okay, well, how do we deal with solving rational equations? Well, essentially, we want to deal with them the exact same way we deal with fractions. We want to get rid of the fraction. So we are going to multiply, in this example, we are going to multiply both sides by the least common denominator, or the least common multiple of both denominators, which in this case would be 2x minus 1, the entire thing squared. Once you've done that, we no longer have a fraction, and we can go ahead and solve this equation, and when we do, we will have what we call proposed solutions. Why are they proposed solutions? Because even though they satisfy this equation, we have to go back to the original equation to make sure that it is still defined for that equation. For example, if any of these two numbers causes the denominator to be equal to 0, then the equation is not defined because you cannot divide by 0, and therefore that solution would have to be excluded. So what we will do is we will check and exclude all. We will check all proposed solutions against the original equation to make sure that the denominator does not equal 0. If it does, then we need to exclude that proposed solution which causes the denominator to be equal to 0. Fortunately, in this particular case, neither of these two solutions causes the denominator to be equal to 0, so the equation is defined for both of these proposed solutions, and they are indeed the legitimate solutions. Okay, well, let's try this with a particular example. And here we have x over the quantity x minus 2 is equal to x over the quantity x minus 2 plus 2. And what's the first thing we want to do? We want to multiply both sides of the equation by the least, or by a common denominator, which would be the least common multiple of x minus 2, and in this case 1, which of course would be x minus 2. So we can multiply this side by x minus 2, and we can multiply this side by x minus 2. Now if we do, we have cancellation over here, and that will give us x. Over here, using the distributive property, we will have x divided by x minus 2 times the quantity x minus 2 plus 2 times the quantity x minus 2. These cancel. We can use the distributive property here, and this will be 2x minus 4, but we'll get there in just a second. Rewriting this, we will have x is equal to x plus, now using the distributive property, 2x minus 4, 2 times negative 2, 4. We have like terms here that we can combine. That will give us x is equal to 3x minus 4. I can then move the 3x term to the other side by subtracting 3x from both sides of the equation. And if I add this vertically, I will have that negative 2x is equal to negative 4. And then I can divide both sides by negative 2. And I have that x is equal to 2. And this is my proposed solution. Now to see if this is actually to see if this needs to be excluded or not, I need to substitute this back into our original equation. If I do, I will have 2 divided by 2 minus 2, which is 0. And that's not going to work. Equals to 2 over 2 minus 2 plus 2. Of course, that will be 2 divided by 0. That's going to, which will be equal to 2 divided by 0 plus 2, since we have a 0 in the denominator here and in the denominator here. This will have to be excluded. Okay, so there, it turns out that since this was the only proposed solution and it is now excluded, there is no solution. And if you were going to enter that into MML, you would enter in the empty set, just like that. Okay, let's do one more. This is a rational equation which will turn into a quadratic equation, which means that solving it might be a little more trickier than the first problem, but nonetheless it should still be doable. Now once again, what we want to do is multiply both sides by a common denominator, and the common denominator is going to be the least common multiple of x minus 2, x, and x squared minus 2x. And you hopefully will notice that that would be equal to, well, x squared minus 2x. Notice that x is a factor of x squared minus 2x, as is x minus 2, because this could also be written as x times the quantity x minus 2, and we actually will use both of those. So what I'm going to do is multiply this side by x squared minus 2x. Then what I'm going to do on this side, instead of using this, I'm going to use this formulation right here, because it's the same. We just say this is the factored version. So I'm going to multiply this side by the quantity x times x minus 2. Okay? So when I do, these will cancel. I'll have negative 2 on the right hand side. For this one, I will have x times x minus 2 times 3x over x minus 2. These will cancel with that, and that will leave me with x times 3x plus 2. And then for the other term, I will have 1 over x times x minus 2. The x's will cancel, and I'll just be left with plus x minus 2. And of course, that will be equal to negative 2. Okay, well, I can do the distributive property here again, and if I do, I will have 3x squared, 3 times x times 3x, plus 2x, x times 2, plus x minus 2 equals negative 2. Okay, now I have like terms that I can combine, and that will be 3x squared. Combining these two will give me 3x minus 2 is equal to minus 2. Okay, and now I can use my add property and add 2 to both sides of the equation. If I add vertically, these will cancel. I will have 3x squared plus 3x is equal to 0. And of course I could divide out the 3, and that will give me x squared plus x is equal to 0. And notice here I have a common factor of x, so I can factor that out, and that will give me x times x plus 1 is equal to 0. So using the zero factor property, we can see that we have two solutions. The first one is going to be that x is equal to 0. The second one is going to be x is equal to minus 1, because this will reduce to, the solutions will be the solution to x being equal to 0, or x plus 1 is equal to 0, which of course would be minus 1. So these are our proposed solutions. So we need to evaluate these two proposed solutions against this equation. So let's take a look at when x is equal to 0. When x is equal to 0, we have 3 times 0, which is 0, plus 2, over 0 minus 2, which is just negative 2, plus 1 over 0. So since this is undefined, the equation is undefined, and there we are. And it also turns out this will be equal to -2 divided by 0 squared minus 2 times 0, which will be 0. Once again, we would have that. So x equals 0 would need to be excluded. Okay, what about x equals -1? Oh, I have a suspicion that will work. For x equals -1, we will have -3 plus 2, which is -1, over -3, over -1 minus 2, which is -3, okay, plus 1 over -1, which is -1, and that's going to be equal to, this is right, -2 divided by -1 squared, which of course is 1, minus 2 times -1, which will be plus 2. Okay? This will reduce to 1/3 minus 1 is equal to -2/3. That will be minus 1/3 minus 3/3, which is equal to -2/3. So this checks out. And we have that our only solution here is -1, and that would be our solution set. Okay, and one application that we have that we can use for this is what we call work rate problems. Now, this is based upon the idea that the rate of work for a particular job is 1 over the amount of time required to do a particular job. So if you can do a job in t seconds, then your rate of work is 1 over t jobs per second, or per unit time, whatever that time might be. Okay, so suppose that we want to know how many jobs can be completed in t seconds. Well, this is called the amount of work completed, and that will be equal to the product of the rate of work times how long you've actually worked while at that particular rate. And that's pretty much all that work rate is. Okay, and as you can see, it's kind of simple. It's similar to the distance formula, except here the rate has to do with the task at hand as opposed to velocity. Okay, so here is our problem. We have one printer that can work twice as fast as the other printer. However, working together, both printers can do a particular job in 2 hours. And the question is, how long would it take for each printer working by itself to do the exact same job? Okay, so what do we need to find? Well, we need to find this. How long could each printer working alone do the job? Okay, so what should we do for variables? Well, let's suppose that we let x be the number of hours it would take for the faster printer working alone to do the job, since we're talking about hours here anyways. If that's the case, then 2x is the number of hours it would take for the slower computer to do the job. Now, if x is the number of hours for the faster printer, then its work rate is going to be 1 over x. For the slower printer, the work rate will be 1 over 2x, which is, by the way, what we have here. Okay, so those are our variables, and now we can use this to write our equation. Now notice that the work rate for the rate of work for the faster computer is 1 over x. The computer has been working for the printer has been working for 2 hours. So the fraction of the job that this printer has worked for 2 hours is going to be 2 over x. Now the slower printer goes at a rate of 1 over 2x. It's been working for 2 hours, so the amount of the job that it could have completed in 2 hours would have been 1 over x. 2 divided by 2x, or 1 over x. And all this has to add to one job. So that's pretty much our equation. It's going to be 2 over x plus 1 over x is equal to 1, or 3 divided by x is equal to 1. That's our equation. So we can rewrite it up here. 3 over x is equal to 1. And then over here, and then for 4 we need to solve the equation. Well, that's pretty straightforward. If 3 over x is equal to 1, that means that x is equal to 3. And that means that it took the faster printer 3 hours to do the job. by itself. If it had to do it by itself, it would take it 3 hours. And then the slower printer would take 6 hours to do the job. And that pretty much is our answer. And that we can basically do a cursory check to make sure it makes sense. And it kind of does, because since both printers are working by itself, they're going to take longer than working together. And of course, the math between the two printers makes sense, because they both because the slower printer, the time duration for the slower printer is twice that of the faster printer. So this does indeed make a modicum of sense. Okay, now we want to talk about equations with radicals in it, but before we do that, we need to talk about a certain property relative to P and Q and powers of P and Q. And what we have here is that if you have basically two expressions or two numbers, this basically says that every solution of P equals Q is also a solution of P to the n equals 2 to the n, Q to the n. And a trivial example of that is, well, let's suppose that x is equal to 2. Well, clearly 2 is a solution of x. Well, it also turns out that 2 is also a solution of x squared is equal to 4. Okay? However, since we raised this to a certain power, this expression has additional solutions. For example, not only is x equals 2 a solution to this, so is x equals minus 2. And that is one thing you have to be careful about when you actually have to solve an equation by raising it to a power to get rid of, say, a radical. Okay, and that's what we pretty much have here. And again, here's another trivial example. If we let at P equals x and Q equals 1, that clearly 1 is a solution, x equals 1 is a solution. Okay, but if we square it, we now have two possible solutions to this particular equation. This one and this one. And to make sure that we have the correct solution for this particular equation, we would need to take these two proposed solutions and test them against the original non-raised equation. Okay, now the other thing we need to think about radicals is that the way that we actually want to solve it is to raise the equation to a power that makes radicals go away. And how do we do that? Well, we're going to isolate a radical on one side, raise the power, and see if there's a radical. If there is, if there isn't, great, we're done. We can go solve the equation, then check all the possible solutions. If there is still a radical, then we just need to do it again until we get rid of all of the radicals. And what does that look like? Well, let's find out right here. Here we have x minus the square root of 15 minus 2x is equal to 0. Now the first thing we want to do is, based upon this, is isolate the radical to one side of the equation. Well, we can do that. We can add 15 minus 2x on both sides, and if we do, we will have x is equal to the square root of 15 minus 2x. All right? Now we can square it to get rid of the radical. And if we do, we'll square that, square this, we will have that x squared is equal to 15 minus 2x. Do we have any radicals? Nope, we're good to go. So now we can go ahead and solve this equation. The first thing that we probably want to do is get this into standard form, and that would be x squared plus 2x minus 15 is equal to 0. It turns out that this equation is factorable because we do have factors of negative 15 that sum to positive 2. Those factors would be 5 and negative 3. So we can rewrite this as x plus 5 times x minus 3 is equal to 0. And if that's the case, then our proposed solutions are x is equal to negative 5 and x is equal to 3. Now we need to test these two. So let's take a look at x equals negative 5. If we have that, we will have negative 5 minus the square root of 15 times 2 times negative 5, which will be plus 10, and that should be equal to 0. Of course, that's going to be negative 5 minus the square root of 25, which is equal to 0. That'll be negative 5 minus 5 is equal to 0, which reduces to negative 10 being equal to 0, which is false. So as a consequence, x minus 5 needs to be excluded. X equals negative 5 needs to be excluded. Okay, what about x equals 3? Well, for x equals 3, we will have 3 minus the square root of 15 minus 2 times 3. That is equal to 0. That is 3 minus the square root of 15 minus 6 equal to 0. 3 minus the square root of 9 is equal to 0. 3 minus 3 is equal to 0. And this works out. So this is the only solution that works the original equation, and our solution set would be 3. So remember, you always need to go back and check. Okay, here is another example. And once again, to solve this, remember what we need to do is isolate one radical on one side of the equation, and then since these are square roots, we want to square. So I'm going to add the square root of x plus 4 to both sides, and that will give me the square root of 3x plus 1, and that'll be equal to 1 plus the square root of x plus 4. Now I'm going to square both sides, and if I do, I will at least get rid of this radical. I will have 3x plus 1. Now here I need to treat this like the square of a binomial, so this is going to be 1 plus 2 times 1 times the square root of x plus 4 plus the square root of x plus 4 squared, which is just simply x plus 4. Okay, so notice I still have the radical, so I have to do this again. But so what I want to do is I want to rearrange the equation so that the radical is on one side, this radical is on one side of the equation, and everything else is on the other side. Now the first thing I can do is a little simplification. I can have 3x plus 1. I have a like term here, that's going to be 5 plus x plus 2 times the quantity x plus 4. Now I can go and subtract 5 from both sides and subtract x from both sides. Adding vertically, I will have 2x minus 4 is equal to, and these cancel, 2 times the quantity x plus 4. I can take this one step further and divide everything by 2. These will cancel. These will cancel as well. I'll have x minus 2 is equal to the square root of x plus 4. Now I could square both sides to get rid of this radical. And if I do, on the right, that should be a square there, sorry. On the left-hand side, I will have x squared minus 4x plus 4, and that will be equal to the square root of x plus 4 squared, which is just x plus 4. Okay, cool. And I'm almost done. I can subtract x from both sides. I can subtract 4 from both sides. Well, they want to do that. If I do, these cancel, these cancel, these cancel. Over here I have x squared, I'm going to write it up here, minus 5x is equal to 0. I forgot the square. There it is. Now, notice I have a common factor of x in here. I can factor that out. X times x minus 5 is equal to 0. And then I will have that x is equal to 0. And now my other solution will be that x is equal to 5. Okay, now we need to test both solutions. So let's take a look, and these, once again, these are our proposed solutions. Okay, well, let's take a look at x equals 0. For the case where x is equal to 0, we will have 3 times 0 times 1, or no, 3 times 0 plus 1, which is 1. The square root of that will be, well, 1, minus 0 plus 4, which is 4. The square root of 4 is 2. You have 1 minus 2 is equal to 1, and that reduces to negative 1 is equal to 1, which of course is false. So x equals 0 has to be excluded. What about x equals 5? Well, 3 times 5 is 15. So we'll have the square root of 15 plus 1 minus the square root of 5 plus 4 is equal to 1. That's supposed to be a 1. Sorry about that. We have the square root of 16 minus the square root of 9 is equal to 1. The square root of 16 is 4. Minus the square root of 9, which is 3, is equal to 1. 1 is equal to 1. So this checks out, and this indeed is a legitimate solution. So our solution set will be 5. Now the next collection of problems that we are going to have are problems with rational exponents. And how do you deal with something like this? Well, essentially what you're going to want to do is notice how this is raised to the 3/5 power, and once again a rational exponent is an equation. The rational exponent is a variable or an expression that is raised to an exponent that is a rational number, a ratio of two integers. And once again, here is an example. Now the way we deal with this is we raise the entire thing to the reciprocal of the exponent, which in this case would be 5/3. And then we'll do the exact same thing here, 5/3. And if we do, well, using the power law of exponents, this will be equal to x plus 5 times the product of 3/5 times 5/3, or just simply x plus 5. And that'll be equal to 125 to the 5/3 power. We can evaluate that as the cubed root of 125. Raise that to the 5th power. And of course the cubed root of 125 is 5. So we're going to raise that to the 5th power. And that is equal to 3,125. Okay, so that's pretty much how it's done. There's only one caveat, there's only one thing that you need to be concerned about. And that is, let's suppose you had something like x plus 5 to the 2/5 power is equal to, say, 25. Oh, maybe 3125. Okay, now to evaluate this one, what you're going to do is you are going to once again raise the entire equation to the reciprocal of that exponent, which should be to the 5/2. And this would be raised to the 5/2. But notice here that your denominator is even. If that's the case, then when you evaluate this, you would still have x plus 5 here using the power rule, but you would need to consider both the positive and the negative value of this particular term. So when the denominator of the exponent is even, we have to actually insert a plus or minus and evaluate plus or minus 3125 raised to the 5/2 power. That's what you would need to do. So keep in mind, if the exponent is negative, or if the rational power that you're raising it to has a even denominator, you need to insert the plus or minus. And we're going to see that right here. So here we have x minus 4 raised to the 2/3 power is equal to 16. So what we have to do is raise this to the reciprocal of the 2/3 power, which will be the 3/2 power. So I'm going to raise this to the 3/2 and this to the 3/2. And if I do, I will have, well, 4x minus 4 raised to the 2/3 power, which is raised to the 3/2 power. That's just simply x minus 4. But on the right-hand side, since once again I have an even value in the denominator of the exponent, I need to rewrite this as plus or minus 16 to the 3/2 power. Okay? And now to evaluate 16 to the 3/2 power, we can write that as either plus or minus 16 squared raised to the, 16 cubed, and then take the square root of that, or we can evaluate this as plus or minus 16 raised to the 1/2 power, or the square root of 16 cubed. I'm going to do it this way because I know what the square root of 16 is. That's just simply 4. So this would be plus or minus 4 cubed. And I also know what 4 cubed is. That happens to be 64. Plus or minus 64. So this equation reduces to x minus 4 is equal to plus or minus 64. And of course we have two equations. That will be x minus 4 is equal to 64, and x minus 4 is equal to negative 64. In this particular case, we will have x is equal to 68, and here we will have x is equal to negative 60. Now we need to see if now we need to evaluate both solutions against the original equation to make sure that they are indeed solutions to this problem, because right now they're just proposed. And so let's go ahead and do that. Let's first take a look at x is equal to 68. Okay, well then that will be 68 minus 4 raised to the 2/3 power is equal to 16. That of course will be 64 raised to the 2/3 power is equal to 16. We can write that as 64 to the 1/3 power, the entire thing squared, is equal to 16. Well, 64, the cubed root of 64 is 4. You square that, you get 16. So this one checks out. Now for x equals negative 60, that will give us negative 60 minus 4 raised to the 2/3 power is equal to 16. That's negative 64 raised to the 2/3 power is equal to 16. And we can evaluate this as negative 64, the cubed root of that, the entire thing squared, is equal to 16. Well, the cubed root of 64 is negative 4. And if you square that, yep, you get 16. So both equations work out, and that's also why when you raise an equation to an exponent that has an even denominator, or a rational exponent with an even denominator, you need to consider plus or minus terms. Okay, and the last thing that we want to talk about today is equations that are in quadratic in form. What does that mean? Well, they're not quadratic equations, but they kind of look like quadratic equations. They're equations that can be written like this. If they can be written like this in some way, then they are quadratic in form. For example, here we have 10x to the 4th minus 7x squared plus 3 is equal to 0. If we let u be equal to x squared, we get this right here. Okay. Similarly, here we have x plus 3 raised to the 2/5 power minus 7 times x plus 3 raised to the 1/5 power plus 12 is equal to 0. If we let u be equal to the x plus 3 raised to the 1/5 power, you guessed it, we have a quadratic equation. So we can solve for u, and then once we find our solutions for u, we can go and solve for x. And we are going to illustrate that with this example here. Here we have 6 over x squared plus 1 over x squared is equal to 2. So what do we want to do? Well, we probably want to let u be equal to x to the negative 1 power. If we do, then we will have 6u squared plus u is equal to 2. We can put that in standard form. 6u squared plus u is minus 2, my bad, is equal to 0. It turns out that this can be factored into 3u plus 2 times 2u minus 1 is equal to 0. And how could you do that? Well, once again, the AC method, you would have 6 times negative 2, which will give you negative 12. You want to find factors of negative 12 that sum to 1, the linear term, and of course that would be 4 times minus 3. Their product is 12, and they sum to positive 1, and then you can basically group your terms, and you'll end up with this. And then our solutions will be u is equal to negative 2/3, and then u is equal to 1/2. Okay, now we need to substitute this back into x. So we know that u is equal to x to the negative 1 power. That means that x to the negative 1 power is equal to negative 2/3. And therefore, x is equal to negative 3/2. Similarly, 1 over x is equal to 1/2, and therefore x is equal to 2. And these are our two solutions. Now it might be good to see if they actually do work out, so let's go ahead and see if we can do that. If we let x be equal to negative 3/2, we will have that 6 divided by, or 6 times x to the negative 2 power is going to be 6 times 4/9. That's basically 1 over 3/2 squared, minus 2/3 is equal to 2. Okay, well, this will be 24/9. 6 times 4 is 24, so we have 24 divided by 9. I can multiply this by 3 over 3, and that will give me 6 over 9. Okay, and that will be equal to 18 over 9, which is equal to 2. So this works out. What about when x is equal to 2? Well, then we are going to have 6 times 1 over 2 squared, which will be 6 over 4, plus 1/2 is equal to 2. Well, 6 over 4 is just 3/2, plus 1/2, that's equal to 4/2, which indeed is equal to 2. So both of these work out. And that is all that I have for this particular video. If you have any questions, please feel free to contact me. This is Bob Boyle, signing off.